Hello, Brian Miller-Hicks here, our continuing series of PowerPoints on Earth science and geology. So we're on to a place beyond our Earth, beyond our atmosphere, into space. The science of astronomy has grown by leaps and bounds within the last century or two. We have reached farther into space than ever before. We've started to explore planets like Mars, Venus, Mercury. We sent orbiters into the far reaches of space. We sent Voyager out there, a couple billion miles. So we've come a long ways in the last century or so. It's hard to imagine, or it's amazing to think that in 1903 the Wright brothers launched their first manned aircraft into the air, and mere 66 years later, hey, we're on the moon. So what's beyond our Earth is so vast, incredibly, unimaginably distant from us in terms of stars and galaxies that are out there. But let me try to bring everything, or bring some of the things, some of the issues, some of the knowledge into focus here. Let's concentrate on our neighborhood, that is our solar system, our sun, our moon, and what is in relative terms nearby. And I want to start by talking about where we were in our mental and philosophical journey to get to the point we are today, where we understand better the planets, the stars, the mechanics of gravity and orbits, all sorts of celestial objects such as black holes, quasars, neutron stars. We didn't know all that stuff a couple thousand years ago during the time of the Greek philosophers. To them at that time, to some of them, the Earth was fixed in the center of the universe. All they could see was the objects that were visible to the naked eye, the sun, the moon, occasionally a planet like Mars, and the fixed stars. So let's begin that. So let's start with a brief history of astronomy, not astrology. Astrology is not astronomy. Astronomy is the science of studying the heavens, studying the celestial objects beyond our atmosphere. Start with a fellow named Claudius Ptolemaeus, otherwise known as Ptolemy. He lived from the year 90 AD, Anno Domini, to the year 168, so a couple thousand years ago. He believed that the universe was geocentric, that we were at the very center of the universe. Geocentric means Earth-centered. Why not? If you stand at a place on the planet and watch the sunrise and the sunset, it seems perfectly logical that the sun is moving and the Earth is standing still. We know better now, but back then that's what they believed. Now Ptolemy did a lot of observations. You can see his little measuring stick here. And one thing he couldn't quite correlate with the idea of the Earth being at the center of the universe. And keep in mind, the universe, as they thought of it back then, was just what could be seen, meaning the Earth, the moon, the sun, planets, and the fixed stars. They didn't know about galaxies. They didn't know about black holes, other stuff like that. So Ptolemy struggled with this. He noticed that for example, the planet Mars, if you center the Earth in the middle, in the center, and the sun out here, and the sun out here somewhere, and you observe the orbit of Mars relative to the Earth and the Sun, he couldn't explain that the planet Mars sometimes seemed to go along this orbital circle and then back up to another position. Couldn't figure that out. He came up with a complicated mathematical and geometric scheme to where not only did planets orbit around the Earth, but they also had orbits within their orbits. These smaller orbits are called epicycles. And that would explain the observations of seeing Mars, for example, and the other planets orbit and then back up and then go back around these little circles. That was cool for a while. Now, this gentleman, Aristarchus, did not believe that the Earth was the center of the universe. He believed the Sun was the center and the Earth and other planets orbited around the Sun. Fast forward a couple thousand, 1,500 years or so, Nicholas Copernicus was one of the first prominent scientists to state that the universe is heliocentric, meaning the Sun is at the center, and the Earth and the other planets and moons orbit around the Sun. Now, he got in trouble with the Catholic Church for this. They thought it was heretical because, of course, we're at the center of the universe. Of course, Earth is the center because we human beings are the best and the most elegant creatures that God ever created in his own image. That was their belief. Copernicus was right about the Sun being at the center. He was not correct about the shape of the orbits of the planets. He thought they were all circular. This fit in with the idea of the universe, of creation, God's creation, the universe, and known universe at that time being perfectly symmetrical and obeying the laws of symmetrical geometry. It wasn't until later that the orbits were known to be elliptical and not circular. Let's go back for a minute to talk about what I was talking about earlier, about the observations that Mars, for example, seems to orbit and then back up and circle around. Ptolemy explained this by using epicycles. But Copernicus figured out that it was because the Earth and Mars orbit the Sun at different speeds. So if you look at this graphic, here is Earth, the blue circles, and the different positions, 1, 2, 3, 4, 5, 6, in the orbit of the Earth around the Sun. If you take Mars, which is a little farther distant from the Sun, we're the third planet, Mars is the fourth. Here's Mars orbiting in a relative position relative to the Earth. So at position 1, position 2, up here, everything seems okay. And then all of a sudden, we observe that Mars reaches position 3 and then backs up to position 4. Okay, so here's position 3. Again, what we might expect to see. But then position 4, Mars seems to back up relative to the Earth. That's because Mars is orbiting at a slower speed around the Sun, and it has a larger distance to travel. Its orbit around the Sun is bigger than the orbit of the Earth around the Sun. So that appears to us that Mars is backing up, but it's just apparent backing up. It's actually moving along in its regular orbit without an epicycle, just appears to be backing up and backing up and backing up because of its slower orbit and greater orbit. It's a phenomenon similar to when you're driving, let's say you're driving down a street and a car is driving next to you, and all of a sudden you accelerate, and the car next to you seems to be going backwards. But it's not going backwards, it's just going forward at a slower speed. So it's an apparent backwards motion that we call retrograde motion. Retrograde motion. This observation helped simplify the orbital scheme to where we didn't need epicycles anymore. We could just explain it by explaining or by pointing out that planets orbit the sun at different rates. The farther out away from the sun they are, the slower the orbital speed is around the sun. And that's because of gravity. Mr. Kepler came along in the 16th century. He was the guy, or maybe one of the guys, that figured out that planets did not orbit around the sun in perfectly circular orbits. They had elliptical orbits. Now, what's an ellipse? If you wanted to draw an ellipse, this is how you would do it. You take a couple thumbtacks and you put a string around them, take your pencil, and you draw and you drag the string around. As you do so, you're drawing an ellipse. A circle has one point that is a center. An ellipse has two what are called focal points that are not quite centered, but that is what you use to describe or draw an ellipse. Okay, so here are Kepler's elliptical orbits, and he understood that the orbits were elliptical and also the orbital speed changed as well. Here we have the sun, here we have the Earth. As the Earth is closer to the sun, it's actually orbiting at a faster rate. Then as it moves away from the sun, farther distance from the sun, it's actually orbiting at a slower rate. It's interesting that the months of summer, the northern hemisphere summer, keep in mind, you might expect the Earth to be closer to the sun because it's hotter up here in the northern hemisphere. But in actuality, in the summer months, the Earth is actually farther away from the sun than it is in the winter months in the northern hemisphere, opposite in the southern hemisphere. This gentleman was a contemporary of Mr. Kepler, more or less. Mr. Galileo Galilei is probably one of the most famous scientists known to history. His very significant contribution to astronomy was inventing and manufacturing, putting together a good telescope. There had been telescopes before Galileo, but they weren't very good. Their lenses distorted what was seen through them. But Galileo perfected, along with some other craftsmen, the art of making lenses for telescopes, and he made a really good one. And with his telescope, he made observations, for example, of Saturn, and actually noted that Saturn had rings. He also made observations of Venus transiting across the sun. He agreed with Kepler that the solar system, or the universe known at that time, was heliocentric, meaning the sun in the center. The next guy in our parade of scientists is another really famous dude. Sir Isaac Newton was an Englishman. Galileo, of course, was Italian, and Kepler was German. I believe he was German. Yes, he was German. Sir Isaac Newton was a very interesting character. Some historians believe he was kind of a jerk. He was very strange in some ways. He was more or less a hermit for many years of his life. And he would do very odd things in the name of science, such as taking a knitting needle and sticking it up into the orbit around his eye to observe the phenomena of flashing lights and so forth. Got to admit, that's a pretty strange thing to do. But he was a scientist with broad interests in astronomy, in optics, in the behavior of light, He did a lot of work with prisms and light beams, and he invented, or was one of the guys that invented, the mathematical science of calculus. So thank Sir Isaac Newton for setting up the science or discipline of calculus, which I, for one, had to study in college and struggled with, but thanks, Isaac. I appreciate it. And of course, one of his most famous contributions to astronomy was the discovery of the force of gravity. He did not invent gravity. He discovered gravity. He discovered gravity as a force and came up with laws of gravity and laws of physics, including laws of thermodynamics. This guy was a pure genius. A very strange genius, but a genius nonetheless. So gravity, as we know, is that force that attracts bodies to each other. The larger the body, the larger the mass, the larger the force of gravity is that that body possesses. So Newton realized that gravity is what keeps planets orbiting around the sun, and gravity is the force that keeps planets from flying off into space. Without gravity, we would just be wandering around aimlessly. But with gravity, and with such a massive object like our own sun, which is gigantic compared to the planets in our solar system, has huge gravitational forces which keep the planets in line, you might say. Okay, let's go beyond the Earth and start exploring our solar system. A solar system, of course, is a system of planets, moons, and other celestial objects, asteroids and such, orbiting around a star. Our sun, of course, is a star. Well, how did our solar system form? We have what's called a nebular hypothesis. We think our solar system is 4-point-something billion years old. We think the universe is around 13.7 billion years old. That's a lot of time for things to happen. So if you look at this graphic, we have up here a nebula, which is a cloud of stars, dust, fragments, elements, with some rotational aspect to all these particles. As this hot cloud of material rotates, starts cooling, starts tightening up into a tighter and tighter cloud, the material at the center of this spinning cloud is the hottest, with the cooler materials and gases in the outer edges. As this continues to cool and condense, the fragments of hot dust and gases begin to condense into what are called planetoids, which formed from these rings of matter orbiting around the central hot star, which has ignited because of the density of the material at the center of the spinning series of clouds. Finally, these planetoids or planetesimals coalesce into objects that we can call planets. And because of gravity, if you have enough mass, gravity will pull that matter into a sphere shape and form planets. So, as you know, we have 8 planets in our solar system. Sorry for you Pluto fans, but Pluto is considered a dwarf planet. So that's the basic idea behind how our solar system formed. Here is a picture of our solar system a little closer up. Sun at the center, Mercury, first planet around the sun, Venus, that should say Venus, Earth, of course, Mars, Jupiter, Saturn, Uranus, and Neptune. Now in between Mars and Jupiter, you see this red accumulation of material in this ring. That's the asteroid belt. So the asteroid belt is composed of rocks, fragments, dust, some ice probably, that never got organized enough to organize into a planet. So it's just loose debris left over from the formation of our solar system, all orbiting around the sun between Mars and Jupiter. The Kuiper belt out here is a collection of fragments as well, a lot of ice, dust, and loose material, way out beyond the orbit of Neptune even. So beyond the Kuiper belt is something called the Oort cloud, O-O-R-T, which defines pretty much the outer limits of our solar system. Beyond the Oort cloud, the sun has no gravitational influence. Our planets are composed of two groups: the terrestrial, Mercury, Venus, Earth, and Mars, or rocky planets, and the Jovian, or gaseous planets, which are Jupiter, Saturn, Uranus, and Neptune. The rocky terrestrial planets near the sun are denser than the gaseous planets. They're called rocky because they're primarily made of rock. They're solid cores. Earth has a solid iron nickel core, and it has a rocky mantle and a crust. Mars as well, although it does not seem to have an active hot core. Venus, of course, has volcanoes and is a hot planet, as is Mercury. The theory is that the gravitational influence of the sun is pulling the denser objects closer to it, and the lighter elements that make up the gaseous planets, like hydrogen, helium, methane, and so forth, were expelled outwards by solar flares or solar. So it's thought that jets of energy or pulses from the sun itself expel the lighter gases and ices, including carbon dioxide and methane ices, to the more or less outer limits of our planetary family, including the gaseous planets seen here. Let's talk about our sun. What do we know about our sun? We know it's a star. We know it's gigantic. It's huge. It's also got a structure to it. It's not just fire. In fact, it's not fire per se. It's, of course, composed primarily of hydrogen and helium. It's got a core, which is very, very, very hot, that radiates energy outwards into, if you will, the sun has sort of a mantle similar to Earth, and it has convection currents similar to convection currents in the interior of the Earth. Of course, convection currents are set up by heat and cold, by temperature differences. Hot material rises, cooler material sinks. Same with the sun. The sun has various features to it. It's got sunspots, which are actually slightly cooler regions of very, very hot gas, and so they appear darker. The outer layers of the sun include the photosphere. The photosphere is what gives us our light, that propels photons out into space so that we can see the light coming for us from the sun. And by the way, the sun is 93 million miles away from us. It takes about 8 minutes for light to get from the sun to us. And the outside of the photosphere is a halo of glowing gas called the corona. Other features include prominence, which are flares or jets of very hot gas fountaining out from the surface of the sun. Spicules are sharp peaks of these kinds of hot gases coming out. The chromosphere is that layer which contains the spicules. just in the outer skin of the sun, if you will. So here's a photo of the surface of the sun. This is a giant sunspot with slightly cooler gas, and there are also areas of magnetic anomalies. This cornflake-looking texture, I think it looks like cornflakes, is what's called each little pocket or flake, if you will, is called a granule. And that again is an effect of hot and cool gas circulating up and down, sort of, I guess, similar to the surface of a lava body in a caldera. The slightly darker is slightly cooler, and then the brighter, hotter material, gas, is lighter in color. Now, because the sun is so bright, we can't see all the features during the daytime, except with special telescopes. If we wanted to see the flares and the hot gas coming out from the sun's surface from the chromosphere, we have to wait for a solar eclipse. And even then, of course, we have to protect our eyes. So you see the disk of the moon blocking the disk of the sun, and these jets of gas coming out. These are the solar flares, and this glowing white area is the corona. Again, the sun's outer corona. Now the sun, again, is a huge body. It's a giant sphere. It's got a lot of energy to it, and it influences our solar system for many, 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 many millions of miles. The sun ejects gas periodically, not just a few thousand miles from its surface, but millions of miles away from it. And these jets of gas attain incredible speeds as they jet towards us and to the other planets. Fortunately, to protect us from a lot of that energy, a lot of that solar wind, the solar wind being the phenomenon that blew the gaseous elements out away to the edges of the solar system and made the gaseous planets, we have a magnetosphere. The magnetosphere actually protects us from a lot of this energy and a lot of this radiation. And we have a magnetic sphere, or magnetic field, because we have a liquid nickel iron core which is rotating and moving and setting up magnetic force field, or magnetic lines of energy. So this magnetic sphere deflects a lot of the sun's energy away from us, fortunately. The other planets and the moon do not have this kind of protection, and they're vastly more affected, significantly more affected by radiation. That's why going to Mars is going to be, that's one issue of going to Mars, is the very high radiation levels on Mars. If we wanted to settle it, we'd have to protect ourselves from that high radiation. Here's another cartoon of solar wind injecting that energy towards us, the magnetic shield deflecting that energy. There are a couple areas where the energy comes through into our planet's atmosphere, and that's at the poles, the North Pole and the South Pole, where the solar wind and solar energy reacts with our atmosphere, interacts with gases in our atmosphere like nitrogen and oxygen. It creates this very, very colorful display we call aurora. Up at the north, we call it aurora borealis. In the south, we call it aurora australis. That gives us these wonderful, colorful displays like this.